Light travels in straight lines. How a shadow is formed. You need light, you need an opaque object, and there's a model, a drawing, which can explain how shadows are. So now, that's the first step. So we understand what we want students to know, the big ideas. The next step is, what would we accept as evidence of understanding? If a student sat in on my class and I taught shadows, and then I wanted to find out, did the students understand the lesson about shadows? What would I ask them to do? What test questions would I ask? What would convince me that they understand shadows? So in the text, in the discussion box, write down, what would you accept for understanding? What should a student be able to say or do or write that you would say, yes, that student understands shadows? Now, we don't have to limit ourselves to paper and pencil tests. We can actually ask them to make shadows. And would it be enough to make a shadow, or do we want them to do more than just make a shadow? So here are some of the things which I think we might agree would show understanding. Students can create shadows at different sizes. Okay, so if a student says, oh, I can make a big shadow or a small shadow, I would say, oh, that's good. Students can predict the changes in shadow lengths or shadow size and check it experimentally. And then finally, students can predict changes in shadow lengths and check using array model and or mathematically. And once we get to this point, that we know the enduring understandings, the big ideas, and we know the evidence of understanding we will accept as people learn this, now we can create the lesson. And so how do we create the lesson? Well, if you wanted to create a lesson on shadows, you could go to a textbook, you could go to the internet, you could ask a colleague, another teacher, how do you teach shadows? But wherever you find this resource, whether it's a friend, a teacher, the internet, a textbook, you ask yourself a certain set of questions. First of all, you say, do I understand the lesson? Because if you don't understand it, you shouldn't be teaching it. Then you ask, is it appropriate for my students? I teach primary school. This is a high school lesson with too much math. Or I teach high school and this lesson is too simple. Then the third question you ask is, do I have the stuff required? Do I have the materials I need to teach this lesson? And then fourth, you ask, does it meet time demands? If I only have 1/2 hour and the lesson takes 4 hours, I can't use that lesson. So these are some of the questions you ask after you find the resource. Now, the very simplest model for a good lesson that I know of is ABC, as simple as ABC, activity before concept. We know from a great deal of literature on how people learn that we have to give them an activity, a phenomena, something to do before we introduce the concept. Now with shadows, you might say, well, everybody knows about shadows. It's like, well, maybe not. So you want to make sure that they have an opportunity to make a shadow. So you give them a candle or a torch, or their phone might have a camera, a light source on it, but a light source, and you can give them a little piece of paper, a Post-it, and a screen, and they should be able to make shadows. So that's the activity before concept. And then the concept, which I want to eventually teach them, is that a shadow is formed because light leaves the star, light leaves the light source. Some of the light hits the screen, which is on the right, and some of the light is blocked by the opaque object. So activity before concept. The activity is play with the shadows, and now the concept is how a shadow is created. But this is not, that's just a quick skeleton of the lesson. The lesson has much more. And we make the lesson better by using not ABC, but the 7E model. Engage, elicit, explore, etc. And we'll go over these. And you might also use, to make the lesson better, the 4 essential questions. And in the United States, we use something called the framework, which is, or the next generation science standards, which are the, a mapping of the kind of things students should be learning in school. So let me show you this framework, because it's not unique to America. It's just, this is the way we put it together. In every lesson, there should be 3 dimensions of the framework in every lesson. Every lesson should have science and engineering practices, cross-cutting concepts, and disciplinary core ideas. Disciplinary core ideas are content. So in our shadow lesson, shadow is the content, shadows and light and things like that. The science and engineering practices are these eight parts of science, but they're all practical. They're all doing something. And if you think about a laboratory experiment, a lot of these make more sense. You ask questions. You develop and use models. You plan and carry out an investigation. You look at the data. You might use mathematics. You make an explanation that makes sense for the data. You engage in argument from evidence. You say, I can explain this because of this reason. And you communicate your information in a report, whether it's an oral report or a written report. So let's make that ABC lesson a little better. So the first thing you want to do in the 7E model is you want to engage the students. So the way I might engage students in the shadow lab is, the shadow lesson, is I might come in and I say, I was outside and I had a big shadow, and then I came inside and my shadow disappeared. What happened to my shadow? I lost my shadow. And this is just to get them thinking about shadows, to give them a little puzzle that they might find interesting, that might excite them. It's just to engage them, and it takes less than 1 minute. I show them a shadow. And then I want to elicit. I want to find out what they already know about shadows. So maybe I ask them a question. Can a mouse's shadow be as big as an elephant's shadow? And I poll the students. I ask them, can a mouse's shadow be as big as an elephant's shadow? As I might ask you now. So in the chat box, in the discussion box, just write down, can a mouse's shadow be as big as an elephant's shadow? Yes, no, or maybe. And so just write that down. Or in class, you might have a thumb up, a thumb down, but just write down yes, no, or maybe. Can a mouse's shadow be as big as an elephant's shadow? And try to answer the way your student would answer, not how you would answer. Okay. And now we start the explore. The explore is for them to make shadows. And I'm going to give them an elephant and a mouse. The little blue post-it is the mouse, and the big red post-it is the elephant. And I ask them, can you make the shadow of the blue post-it, the mouse, bigger than the shadow of the elephant? And they take their light source, and they do that. We talk to them about safety. And then I give them 8 minutes to do this. And all of the groups start making shadows, and they start moving the post-its and moving the light and moving the screen until they can show me that the mouse's shadow can be bigger than the elephant's shadow. And then I ask them to explain. How can I make the shadow larger? The claim is to make the shadow larger, I can, and the students write down what they found from their experiment. To make the shadow larger, I can move the screen further away. I can use a larger object. I can move the light source closer. I can move the object away from the light source. How can we explain this? And so now I have to help them with the explain. So the explore was this. Then they explained to me how to make a shadow larger. And now I'm going to also explain to them. Light travels in straight lines. And I asked them if they had any evidence for this. And some students may say the sun rays going through the clouds shows light traveling in straight lines. Or the laser, in a laser light show, you can see the light travels in a straight line. Once we know that light travels in a straight line, that's all the physics about light we need to explain shadows. You see, this light source gives off light in all directions. The star gives off light in all directions. The light going to the left, we don't have to worry about. But ray number 1, this straight line of light, goes all the way from the star all the way to the screen. Light ray number 2 goes all the way to the screen. And everything in between 1 and 2 goes all the way to the screen. Number 3 gets stopped by the post-it. Number 4 gets stopped by the post-it. Number 5 and 6 get stopped by the post-it. Number 7, it goes all the way to the screen. And number 8 goes to the screen. And so what we see is that there's light between 1 and 2 and light between 7 and 8, but there's no light between 2 and 7, and that's the shadow. So the students now have a model, this ray diagram model, to explain what creates a shadow. And then we go back to an explore. We want the students to draw these ray diagrams now. But they're going to draw the ray diagrams as practice, but also to look at their claim. So let's say their claim was to make the shadow larger, I can move the screen further away. If so, then we ask students to draw 2 ray diagrams. You'll see the light source, the star, is in the same position in the top and the bottom. The post-it is in the same position, top and bottom. But in the top one, the screen is close, and the bottom one, the screen is far away. The students said that they saw when they did the experiment that in real life, if you move the shadow, make the screen further away, the shadow got larger. In our ray diagram model, does the shadow also get larger if you move the screen? And it does. But now we ask the major question. This is the big question in science, not just in the shadow lab, in every single thing we do in science. Does the model produce the same results as the experiment? So in the model of the shadow, if the screen moves further away, the shadow gets larger. In the experiment, when you move the screen further away, the shadow got larger. And so since the model produces the same results as the experiment, we feel very confident that we understand how shadows are formed. And then, after a moment of feeling so good, we get into trouble. Because somebody says, wait, there are fuzzy shadows. There are shadows which aren't so crisp, which have these fuzzy edges. And in science, when that first happens, when a scientist says, you know, you've explained shadows well, but I've seen fuzzy shadows, everybody else says, no, you didn't. There's no such thing as a fuzzy shadow. Our model predicts sharp shadows. At 2, the shadow begins. At 7, the shadow ends. There's no fuzzy shadow. But this person says, but I saw it. And everybody says, no, go home. You didn't, no, you didn't really see it. But then another scientist, another person will say, I found the fuzzy shadow also. And then I also found the fuzzy shadow. I found the fuzzy shadow. And now we have a problem. Because our model can't explain the fuzzy shadows, but everybody is seeing fuzzy shadows. So we get worried. We don't want to throw out our model, but we might have to. That's how science progresses. In this case, with the fuzzy shadow, it turns out that we can use the same model. You see, you get a fuzzy shadow because the light source is not just one star, one point, but it's actually extended. It has a width to it. So the top part of the light makes a sharp shadow, like we've seen. The bottom part of the light makes a sharp shadow. And when you have the whole light source on, you can see that in the middle, where it says no light, that's the dark shadow. But then just above it, you have light from the top part of the light bulb, but not the bottom part of the light bulb. And at the bottom, below it, you have the light from the bottom part of the light bulb, not the top part of the light bulb. That's the gray part of the shadow. So you have black, gray, and then white. And everybody says, oh, thank goodness, in the elaborate, we now can explain the fuzziness. So everybody feels much, much better about all of this. And then we elaborate further. We say, okay, how can we apply this to something? So let's say we're in the theater and we want to produce a Thai puppet show with live people, or with shadow puppets. And the monster in the theater show must be 3 meters high, but we don't know if the actor is 1.5 meters or 1.8 meters. What do we do? And the student should say, oh, if they're 1.4 meters, they should stand in one location to make a 3-meter shadow. But if it's 1.8 meters, they just stand in a different place with the same light source, and they'll make a bigger shadow. They'll make the 3-meter shadow. Or we ask about colored lights. Are all shadows black and white? And then we can extend it. That was the elaborate. And now we can extend the information and say, oh, let's talk about the big shadows now. Instead of a light source on the left, a post-it in the middle, and a screen on the right, let's have the sun as the light source, the moon as the post-it, and the earth as the screen. And we can get an eclipse of the sun from some places on earth, because some places on earth are in the shadow. So what's the science content the students have learned? They learned that light travels in straight lines. They learned how shadows are formed experimentally. They learned a model of light. They learned how to make shadow formation using the ray model. They found the experimental evidence was consistent with the model. And they found out about fuzzy shadows, the umbra and the penumbra. And they found out that sometimes you have to modify your model. Then they had engineering and technology content with the theater design. And let's look at the 3 dimensions of the framework, at least one of the dimensions, the science and engineering practices. One of them is developing using models. They did that. Here's the model. The model was extended. Now, just for your edification, for your education, if I had a solid steel ball, you would expect the shadow to be a solid black sphere, black circle. And in the 1800s, there's a physicist who said, no, I don't think the ray model of light is correct. Light behaves as a wave. And then somebody else said, wait, if it behaves like a wave, then this guy Poisson, who was a very good mathematician, said, then there would be a dot in the middle of the shadow. The light would go around the edges of the steel ball, and there would be a dot in the shadow, and everybody said, there's no dot in the shadow, it's always solid black, go home, your wave theory is wrong. And then 6 months later, Fresnel found the spot, the white dot in the middle of the black shadow. And so now you can't use a ray model. The model of light does have to change. Using math and computational thinking? Yeah, there's math in this if you look at ratios or triangles or geometry for higher level students. And engaging in argument from evidence? Yes, they did that. They said the claim was, to make the shadow larger, I can move the screen further away. And they showed what evidence they had for that. So we used understanding by design to frame the lesson. We then used the 7E model to make it a better lesson. The 4 essential questions we're not going to talk about today. That's another lesson. That's another talk. And the framework and NGSS, you saw the science and engineering practices at least. So let's get back to our teacher leadership program. These teachers would teach the lesson at the primary level, at the middle level, and at the high school secondary level. They would all teach a similar lesson. It's different, but it's the same topic. In the spring, they'll do it in one grade. But what they'll do is they will choose in their course of study developing and using models. So that's their course of study, developing and using models with shadows. And maybe their research article is checking for student understanding. They teach the lesson, they videotape the lesson, and then they have a face-to-face group meeting. So let's take a look at the videotape for lesson. I have a lesson here, just 30 seconds of a lesson.
All right, so somebody, I can call anybody, because we'll order that. Tell me how a mouse is shadowed and bigger than an elephant shadowed. Go for it.
Well, I think that would depend on either the sun or the light.
What I'd like you to do in your groups, and 2 people in a group can do this, is I'm going to give you a mouse and an elephant, little and big. And I want you to create something with this one light at your table and call me over when you get this has as big a shadow, the same size shadow as this. The mouse has as big a shadow as the elephant. Here, 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 here.
Keep going. Keep going. Almost. Because it's going to make
The next one up. Shadow.
So this was just, what they would do is they would watch the videotape. You watch the videotape with me. It's informed by the course of study, so they know it was about shadows, it's about model building, and it was about checking for understanding. The teacher, they come together and they read this, they watch the video, and they complete a feedback form. And then they have a meeting where they give warm and cool feedback. This is what we liked about the lesson, this is what we didn't. We could see you were checking for understanding. We saw this, we saw that. And then the teachers discuss the lesson. Then the next teacher, the following week, will teach the lesson, and they'll do the cycle again. So here's a sample of some teachers debriefing.
Now we're back on track. So I just thought that was a really great transition.
I like how you use the computer in the classroom, that you were able to do type up the comments and questions because they have to put into this there in order. That's a nice. I think you modeled well when you were rewarding or helping the students with the questions. You used the word how. So they got accustomed to using that also, because that gave them questions to do yes or no.
So you'll notice the teacher was listening. One teacher was in the corner listening. All 3 were providing feedback. He's just quietly, not responding to them, listening and taking notes. So every month we have meetings of the cohort where we talk about other aspects of adult learning and things like this. In January, that team that you saw will present to the rest of the team, the other 16 teachers, what they have learned about teaching shadows, what they have learned about checking for understanding, what they have learned about models in science. And so what we've learned from this project is that collaboration, leadership, relationships, but mostly right at the bottom here, learning from each other. Teachers learning from each other. And if I had one conclusion to say is, well, in that group of 4, who was the leader? And they say, oh, no, we were all the leaders at different times. And that's one of the keys to being a teacher leader. Not to say, I'm the teacher leader, listen to me, but can we work together and take turns being the leader so we can all learn from one another? So what we've done, what you can do. It's a big program, but what you can do next week, if you like, after this conference, is you can create vertical teams of 4 teachers, either primary, middle, and secondary schools, or you can choose 4 teachers in one grade level. Determine a course of study. What's a topic that you might want to all try to teach? Find a research article on cooperative learning, checking for understanding misconceptions, and maybe choose a science practice like models or using data or communicating or asking questions. What I want to leave you with is the idea that you're the experts. The teachers are the experts. The teachers are the ones who can find out what works. They can test it in the classroom because you're in the classroom. You can stimulate the research community with your findings. You, the teachers, are the leaders of the educational community. As leaders, as teachers, as leaders, we change people's lives. We communicate the beauty in the world. We help students reach their potential. Margaret Mead, the great anthropologist, said, "Never doubt that a small group of thoughtful, committed citizens can change the world. Indeed, it's the only thing that ever has." We are changing the world and making it a better place. So let me stop sharing. And I left 10 minutes. Okay, I stopped sharing the screen here. And so let me get rid of this. And now I think I'm back. And okay. So I left 10 minutes for questions, and it's exactly 10:50. So we're right on time, and everything is good. I couldn't see you. I can't see any of you, so I'm so glad. Are you still here? Are you still here?
All right. Thank you for your wonderful presentation, Dr. Eisenkraft, and for sharing with us your knowledge and experience. Honestly, I didn't know that the 7Es format can assume a different sequence. It can be flexible, re-explore like that. And that's great. So please enjoy your break. Thank you very much, and good day.